My name is Marcoen Cabbolet. I'm a research affiliate at the Free University of Brussels, and welcome to my talk, Berkelian Idealism regarding properties in orthodox quantum mechanics and implications for quantum gravity. I would like to begin with a head warning. This talk contains philosophical arguments. So, in physics circles, the prevailing opinion seems to be that philosophical arguments can be completely avoided. And, well, of course, I agree that philosophical considerations are irrelevant when we are doing calculations or performing experiments. But I sincerely believe that it is a mistake to think that philosophical reflection is irrelevant also at the conceptual level. And this talk is at the conceptual level, so I will argue that quantum gravity is ruled out by an essential feature of the concept of a quantum. In this talk I will first give a brief overview of the idealism of George Berkeley. Second, I will show which form of Berkelian idealism is contained in orthodox quantum mechanics. Third, I will show what the implications are for quantum gravity. And finally, I will state the conclusion. Okay, George Berkeley was a philosopher and a bishop who lived from 1685 to 1753. In his 1710 book, a treatise concerning the principles of human knowledge, he published the now famous dictum, esse est percipi, to be is to be perceived. This refers to the idea that a thing exists if and only if it is observed. And Berkeley was the one philosopher who developed this idea to completeness, and he concluded that there is no such thing as material substance that exists outside the mind. So all perceived objects are nothing but ideas in the mind of the observer. So that immediately raises the question whether Berkeley's idealism isn't in fact a solipsism, where the self is the only existing reality and all other persons are nothing but ideas in the mind of an observer. So for me then, all of you are nothing but ideas in my mind, and for each of you, I am nothing but an idea in your mind. But Berkeley rejected this solipsism. The ideas are the work of God. So the world is given as a collection of ideas to all conscious beings, and therefore the world has an objective value, but still it is not a material thing. In a nutshell, that is the idealism of George Berkeley. Nowadays it is considered to be highly unlikely. To go to the relation between Berkelian idealism and orthodox quantum mechanics, I will focus at the core principle that a thing exists if and only if it is observed. So the only if part, it reads that a thing exists only if it is observed. So Berkeley denies that the thing exists if it is not observed. Yeah? But orthodox quantum mechanics, on the other hand, does not deny that the quantum exists if it is not observed. The state postulate, namely, dictates that a quantum state is represented by the wave function psi with norm 1, and the statistical interpretation hereof by Max Born from Wroclaw. The statistical interpretation means that orthodox quantum mechanics predicts with certainty that the quantum will be found somewhere if we look in the whole space. Now, the definition of completeness of a theory entails that a thing predicted with certainty has a counterpart in reality. So if we view orthodox quantum mechanics as a complete theory, we implicitly take the position that the quantum has a counterpart in reality, even if it is not observed. So it is not the case that the quantum exists only if it is observed. So we do not have the only if part of Berkeley's principle. So in orthodox quantum mechanics we have no Berkelian idealism in its fullest sense. Now the form of Berkelian idealism that is contained in orthodox quantum mechanics is a Berkelian idealism regarding properties. So a quantum has a property x with quantitative value x if and only if the property x is measured with outcome x. Yeah, so Berkeley's principle was that the object exists if and only if it is observed, but here the property exists if and only if it is observed. Okay, this follows from two postulates of orthodox quantum mechanics. The first is the standard property postulate. A quantum has a property x with value x if and only if it is in the eigenstate x of the associated operator x. Yeah? So the only if part forbids us to say that the quantum has the property if it is not in this eigenstate. The if part, on the other hand, guarantees that the quantum does have the property if it is in this eigenstate. The second is the projection postulate. If the property x is measured and the value x is obtained, then, upon a measurement, the quantum is in the eigenstate x. Now this is the only postulate of orthodox quantum mechanics that tells us how the quantum can get in this eigenstate required for having the property. So absent special preparations, it is ruled out that the quantum gets in this eigenstate without a measurement. Yeah? And together that yields this Berkelian idealism regarding properties, and that is an essential feature of the concept of a quantum. And it is a feature that remains intact when we start making relativistic corrections. These corrections only concern the measured value of a property, but these corrections do not concern the criterion itself for when the quantum does or doesn't have the property. Now, that being said, I now go to the implications for quantum gravity. A fundamental principle in this context is the principle of curvature. Sorry. Space-time is curved due to the energy of objects as expressed by Einstein's field equations. This principle is backed up by empirical evidence. So if we want to develop a quantum theory of gravity, we'll have to somehow recontextualize this principle in the framework of quantum theory. And that's where we stumble on a problem. On the one hand, namely, space-time is not a substance, it is not an ether. Therefore, it is not an object that is subjected to the Berkelian idealism regarding properties. So at any spatio-temporal position Tx, space-time has a definite curvature, regardless whether we make a measurement or not. But on the other hand, the quanta that populate the universe only have a definite energy upon a measurement of that energy. That's the Berkelian idealism regarding properties. Yeah? So no measurement, no cause of curvature. Yeah? So space-time always has a definite curvature, measurement or no measurement. And the cause of curvature only exists upon a measurement. That's the problem. To illustrate the problem, this picture shows a system of 5 quanta at a given time, t. Horizontally, the spatial x-axis, vertically, the spatial y-axis, the z-axis is suppressed. These blurred spots represent the probability distributions of the quanta, with a darker tint indicating a higher probability of being found at that position. So at this spatiotemporal position, spacetime does have the property curvature with a definite value g, regardless whether we make a measurement or not. But without a measurement, these quanta do not have the property energy, which is supposed to be the cause of the curvature here. So therefore, the principle of curvature cannot be recontextualized in the framework of orthodox quantum mechanics. An example of a pragmatic approach to the problem is to let the curvature emerge from the expectation values of the momenta of the quanta, as expressed by this formula. Mathematically it's well defined, so one might think that it solves the problem. However, these expectation values refer to expected outcomes of measurements. These are not properties that the quanta have. So this solution is conceptually incoherent. It is not a solution at all. So taking the principle of curvature as a fundamental principle, the general conclusion is that a theory of gravitation is not possible in any framework implying Berkelian idealism regarding properties. This yields a modus tollens kind of argument against quantum theory. So we have seen that the Berkelian idealism regarding properties does not work for the principle of curvature. So from the pragmatic point of view, it is not true. So we have not B. So if we then have a quantum framework that implies this Berkelian idealism regarding properties, then we are forced to conclude that the quantum framework isn't true either. Now, Mahoney concluded from a social experiment in 1977 that over 50% of scientists doesn't recognize modus tollens as a valid reasoning form. Assuming that physicists are not excluded, then probably more than half of this audience doesn't recognize the present argument as a valid argument against quantum theory, but I believe it is. Personally, I do not believe in quantum theory. I do not believe that this problem can be solved, but if nevertheless a solution exists, I would be interested to learn about it. So, thank you for your attention.
Questions? Solutions?
But general, also at classical level, general relativity is leading unavoidable to a singularity. What happened in a singularity? This is a problem still alive in your approach. There is Penrose-Hawking theorem demonstrating that in all collapse configuration of the world, you obtain a singularity in certain condition. So, if you quantize gravity, there is a possible way out. String theory has an idea, quantum gravity has an idea, asymptotic safety has an idea, but what is the conclusion of this approach?
It is not approach, it is merely an identification of a problem. Either orthodox quantum mechanics has to go, or the principle of curvature has to go, but you cannot have both.
So I think that maybe there could be different solution of the problem, because I never heard about direct measurements of curvature. However, we can measure fields, and we can measure relation between fields. So maybe we shouldn't even ask about the existence of curvature, because okay, I never heard about a well-defined I cannot. We shouldn't treat curvature as an observable. We can just think about curvature as a something that we can define as a existence of a curvature if there is some relation between observables, not as a thing itself. So I think there is no problem at all.
Well, my comment goes a bit into the same direction because, I mean, what is curvature of space-time? Curvature of space-time we experience as gravitation. And if you don't test it, or if you don't have an observer, we can also not tell anything about the curvature. So curvature is not an absolute object which exists somehow in an absolute space-time, but it exists through the action between bodies. And therefore there's absolutely no problem about this argumentation. But if you talk about carrying energy or gravitational waves, you observe them. You have a test body.
Yeah, you have the deflection of a photon has also been observed.
Yes, exactly. Yes, we can observe photons, not the curvature.
Let's give the speaker a chance to reply.
Yeah, if the path of the photon deflects, you explain it by curvature. So the point is that the principle of curvature, as published by Einstein, that the space is curved due to the objects, due to the energy of the objects. Yeah. If you say we deny that curvature exists, yeah, of course that's a way around the problem. But then the problem is non-existent. Yeah, but that's what I said. I said either the principle of curvature has to go, or orthodox quantum mechanics has to go, or both have to go. Yeah, yeah.
I think we have to break this off. There's still time for private discussion. Let me just try one slightly different comment. So what you refer to, you wrote down an equation which is usually associated with something called semi-classical gravity. So you have the Einstein tensor on the left-hand side, and then some kind of quantum stress energy tensor on the right-hand side. And people in physics have criticized this approach a lot because of physical inconsistencies. It's considered an approximation, but nobody really knows how good it is. So I don't think anyone would say that this is a fundamental theory of quantum gravity, so one could use your arguments in a positive way and say that if we eventually find out what quantum gravity is, somehow space-time has to be turned into a substance, so there has to be a more concrete measurement of space-time constituents or something like this. And then you can apply the usual quantum rules to measurements of space-time properties like curvature. So
yeah, then you're saying the principle is not fundamental.
Not in this approach, not in the approach you've been referring to. So a more fundamental quantum gravity theory would probably modify your equation and make it more fundamental for reasons which you have brought up.
But that's my point. You will have to modify it in any way,
right.
or else you...
Yes.
Yeah. So that was my only point.
Right.
Just one.
And I think there are physical arguments as well.
The one is incompatible with the other. That was my whole point.
Right.
Yeah.
Okay, we have to move on. Thank you again.